Hi students, today we'll discuss about the molecular orbital structure of pyridine. So we already studied the molecular orbital structure of pyrrole, furan, thiophene, and I hope it will be easier to you now to understand the molecular orbital structure of pyridine. So pyridine is the six-membered heterocyclic compound. So this is the structure of pyridine. Okay, and if you write the molecular formula of pyridine, that is C5H5N. C5H5N. As usual, here also both carbon and nitrogens are sp2 hybridized. Both are sp2 hybridized. You all know electron status when they are sp2 hybridized. So for carbon atom, the atomic number is 6 and its electronic configuration in ground state is 1s2, 2s2, 2p2. In the same electronic configuration in its excited state, that is 1s2, 2s, 2p. Here one of the 2s electron will shift to the 2p electron, that is 2s1, 2p3. As usual, inner orbital does not involve in hybridization, so that's why 2s orbital and 3 2p3 orbitals. So this is 2s, these are 2p. You know it is 2px, 2py, 2pz. So each of them are containing an unpaired electron or single electron. Here this 2s, one of the this 2s orbital and two of the 2p orbitals involving in sp2 hybridization. So those will become with equal energy and identical shape. That's why I'm writing with condensed structures. So these three are 3 sp2 hybrid orbitals, and each of them are containing unpaired electron. And this 2p z or 2p any one 2p orbital, that is also containing unpaired electron, which is unhybridized, p orbital. So for nitrogen atom, the atomic number is 7. The electronic configuration in ground state is 1s2, 2s2, 2p3. The same electronic configuration in excited state is 1s2, 2s1, 2p4. One of the 2s electron will shift to the 2p orbital. So here this also inner orbital does not involve hybridization, and this 2s, 2p, 2px, 2py, 2pz. So here 1, 1, 1, 1. I'm not actually according to Hund's rule, but one of the electron will paired in the hybrid orbital itself. So now this 2s orbital and two of the 2p orbitals, they form hybrid orbitals. These three are 3 sp2 hybrid orbitals, and this is the unhybridized p orbital. So one of the sp2 hybrid orbital is containing pair of electron, and this unhybridized p orbital is containing unpaired electron. Unhybridized p orbital. Why this change? Because here you can see carbon are 5, so each carbon is giving 1 electron, so mean 5 electrons, and this nitrogen is 1, that's why this nitrogen also give 1 electron during the formation of pi bonds. So that will be involving 6 pi electrons, so that forms the most stable sextet form. So that sextet configuration is very much needed to give the stability to the ring, that is pyridine. So that's why one of the sp2 hybrid orbital is paired. Here it is unpaired, unhybridized p orbital. So I'm just summarizing this electron status over here. So for carbon atom, it is sp2 hybridized, and all three sp2 hybrid orbitals are with unpaired electrons. Unpaired electrons, and there is one unhybridized p orbital, one unhybridized p orbital, that is also with unpaired electron, with an unpaired electron. And for nitrogen atom, that is also sp2 hybridized, and here also two of the sp2 hybridized. Okay, two sp2 hybrid orbitals with unpaired electrons, and one sp2 hybrid orbital with pair of electrons. Pair of electrons. And there is also one unhybridized p orbital that is also with unpaired electron. So I hope you can see till there, end of the board. Okay, this is the status of the carbon and nitrogen when they are sp2 hybridized in the pyridine. So all three hybrid orbitals of carbon are containing unpaired electron, and one of the three sp2 hybrid orbitals of nitrogen is containing pair of electrons. And this pair will not forming any bond, already it is paired. That's why it will remain as a non-bonding pair of electrons that I have represented outside the ring. So now we'll see the molecular orbital structure for formation of sigma bond. Formation of sigma bonds. Formation of sigma bonds. So there are 5 carbon atoms and 1 nitrogen atoms. I'm going to write here. So carbon, 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 and nitrogen. And each of them are sp2 hybridized. So as you already know, sp2 hybridization means the geometry will be trigonal planar with bond angle 120 degree. So one of the carbon with same sp2 hybrid orbitals will overlap with sp2 hybrid orbitals, each of them containing unpaired electrons, and they'll get paired up and forming sp2 sp2 sigma bond, and this overlapping is sp2 sp2 overlapping. Okay, the another remaining orbital sp2 hybrid orbital. So here also the same thing happens with this same carbon. All carbon carbon sigma bonds are formed by sp2 sp2 overlapping. So these all are sp2 sp2 overlapping only. The same way, the one of the hybrid orbital of nitrogen which are containing unpaired electrons, they also will overlap with the sp2 hybrid orbitals of carbon and forming carbon nitrogen bond, sigma bond, that is cn sigma bond. Here the nitrogen here also it is also pairing up with the carbon orbital. So this is also sp2 overlapping only, and this nitrogen is still containing an sp2 hybrid orbital with a pair of electron that do not involve in any kind of bond formation. So hence it is known as non bonding pair of electrons, or also lone pair of electrons over the nitrogen atom. This is and still each carbon is containing an hybridized sp2 hybridized orbital with the unpaired electron that is going to form a sigma bond with hydrogen, ch sigma bonds. So the s orbital of the hydrogen overlapping with hydrogen, sorry, sp2 hybrid orbital. So this is sp2 s overlapping forming a ch sigma bond, same with all the 5 carbons. sp2 s overlapping forming carbon hydrogen sigma bond. Carbon hydrogen sigma bond. So here we can see 3 types of sigma bonds. The one is carbon carbon sigma bond, another one is carbon nitrogen sigma bond, another one is carbon hydrogen sigma bonds. In this carbon nitrogen sigma bonds are formed by sp2 overlapping, and this ch sigma bond is formed by sp2s overlapping. So this is the molecular orbital structure of pyridine for the formation of sigma bonds. And this is actually equivalent to this structure. I'm going to write here. This is equivalent to the structure. There is sigma bond between carbon and carbon. Carbon. This is one of the sigma bond. Here also carbon sigma bond. Carbon nitrogen sigma bond with the pair of electrons, lone pairs. Here is a carbon nitrogen sigma bond, carbon sigma bond, carbon sigma bond. And also each hydrogens are forming sigma bonds with hydrogens, hydrogen. This is the equivalent structure of this one. This is the molecular orbital structure, that is the bonding structure we can show represent here over on the board. So this is the for the formation of sigma bonds. Now we'll discuss for the formation of pi bonds, because we can see here there are 3 pi bonds in the ring. Yes, formation of pi bonds. As you all know, the pi bond is formed always after the formation of sigma bonds. So that's why I'll take this structure, the structure after the formation of sigma bond. So carbon, nitrogen, carbon, and the nitrogen is still with the hybrid orbital with a pair of electrons. We can represent with the dots or that arrows. Okay. So here, after the formation of sigma bonds, each carbon and nitrogen still have an unhybridized p orbital, that is present perpendicular to the plane of the sigma bond. Yes, and each of them are containing with an unpaired single electron. So I'm just writing opposite spins, because when they are only opposite spins, then only they will get paired up. So these all p orbitals, unhybridized p orbitals with the unpaired electrons will show sideways overlapping or lateral overlapping, that is going to form pi cloud or pi bonds in the pyridine. So always you know the head-to-head overlapping or axial overlapping forming sigma bonds, and here the sideways are lateral overlapping. This upper lobe, same upper lobe forming a pi cloud over the sigma bond. The same way the lower lobe will show a sideways or lateral overlapping, that is forming a pi cloud. So there are totally, this is the final molecular orbital structure of pyridine. So here you can see each carbon will give 1 electron and also nitrogen will give 1 electron. So totally here we can see 6 electrons in the pi bond formation. So 6 pi electrons, and all these 6 pi electrons are delocalizing electrons. So that is also giving the aromatic property to this compound. This structure is now equivalent to this structure. This one, or the same like this, or yes. Okay, and still there is one lone pair of electrons on nitrogen. This is about the molecular structure of pyridine. Students, usually the questions are framed like write the molecular structure of pyridine and mention its aromaticity. Usually the aromaticity is also been asked along with the pyridine. So as we already seen aromaticity for all other compounds, that is pyrrole, furan, and also thiophene. So let us discuss that thing also here. So you already know that four criteria should be fulfilled by any compound to show the aromaticity. The first criteria is that the compound should be cyclic and planar. You know this pyridine is also cyclic and planar. So if the start ring with nitrogen, it ends up with nitrogen, so it's a cyclic. And also as it is sp2 hybridized, it shows the trigonal planar geometry, hence it is planar. So hence the first criteria is fulfilled. The second criteria is it should have a delocalization. It should show delocalization of pi electron. Delocalization. So here we have just seen that 6 pi electrons. So that is a sextet. All sextet sextet is always a strong or giving a strength or stability to the compound. So 6 pi electrons are involving in delocalization. So it shows resonance. It's a completely conjugated system that we can see also resonance structures of this pyridine when we discuss the reactivity, especially the electrophilic substitution reactions of pyridine in the next class. So this is also fulfilled by the pyridine. The third one is it should obey Huckel's 4n plus 2 pi electron rule. As you already know, there are 6 pi electrons and one ring, so n equals to 1. So 4 into 1 plus 2, that is equals to 6 pi electrons. So you all know any compound which is cyclic and planar and showing completely conjugated system with 6 pi electrons or 10 pi electrons, 14 pi electrons, 18 pi electrons could be aromatic. So here it is showing a 6 pi electrons, hence it is also aromatic and obeys the Huckel's rule. Hence it fulfills the third criteria. When it comes to the fourth criteria, that it should undergo electrophilic substitution reaction. The compound should undergo electrophilic substitution reaction. As you all know, for electrophilic substitution reaction, there must be at least one hydrogen atom to replace. So here also we have 5 hydrogen atoms. So those 5 hydrogen atoms can be replaced by any other electrophile. So hence it may show electrophilic substitution reaction. Yes, but there is one problem in this compound. It is not much easily undergoing electrophilic substitutions. So there are 2 other reasons. So that is also been asked in exams, why pyridine does not undergo electrophilic substitution easily. But pyrrole, furan, thiophene are easily undergoing electrophilic substitution reactions. But this pyridine is having difficulty in undergoing electrophilic substitution reactions. Let us see that. The one reason is that, if I give the reason, yes, here you can see the structure. Nitrogen. So this pi cloud is nitrogen is, as it is more electronegative element, which can attract this pi electron towards it, so hence there is a partial positivity may occurs on each carbon. There is a partial positivity may occur on each carbon. So when there is a positivity, so the hydrogen cannot be removed because hydrogen is also positive. Understanding? So hydrogen cannot be easily removed. Already they are showing positivity. So if it is able to remove that hydrogen, that compound will become unstable. So as the nitrogen atom is more electronegative, hence this compound will always repulsive when it undergoes electrophilic substitution. So it cannot easily give that hydrogen electrons. Okay. And the second reason, there is also one more reason. First reason, as this lone pair is there, it is more active. It is more active. It is actually here when an electrophile is introduced. So this electrophile, instead of replacing the hydrogens at the carbon, it will attack on the nitrogen atom. It will attack on the nitrogen because it is having negativity, because lone pair of electrons are over there in the nitrogen. So hence it is going to form this compound. Electrophile with the positive charge. So this is going to form an ion. So this ion is pyridinium ion. This pyridinium ion, as it is a positive charge, it shows resonance also, hence it is become also stable. So hence here this electrophile, instead of replacing the hydrogen, it will be attacking the nitrogen atom. Hence these two reasons are actually making this pyridine to not undergoing these electrophilic substitution reactions. But at vigorous conditions like high temperature, high pressure, this pyridine also can undergo digestion reactions. Hence it is also considered as aromatic. It is also considered as aromatic. Pyridine is also one of the aromatic compound. But these are to the two reasons which is definitely and usually most commonly asked in your exams. Why pyridine does not undergo electrophilic substitution reaction? The first reason is the pyridine is more electronegative element which pulls all the electrons, pi electrons towards itself, and it is making the hydrogens to remove from the compound is difficult. And the second reason, when the electrophile is introduced, electrophile directly attacks the nitrogen because it is carrying a lone pair of electrons. So yes, not like this here. Yeah, the arrow mark should be towards the positive charge. Okay. So these two reasons make pyridine less active or less reactive towards electrophilic substitution reaction. This is about the aromaticity, but pyridine is also completely aromatic, though it has some difficulties in the electrophilic substitution reactions. Thank you. Thank you for watching. And as usual, please like the video and subscribe to my channel and hit the bell icon to get the next updates by me. Thank you.